So the next speaker is Runar Berge. He is an associate professor at Volda University College, where he just started after ending a postdoc at Norse. And he is going to talk to us about a module in MRST that he has developed. I think he started as part of his master's thesis, and he has also continued developing that module afterwards. So the talk is called the UPR module, Unstructured PEBI-grids Conforming to Lower Dimensional Objects. So Runar, the screen is yours. Please go ahead.
Thank you, Øystein. As you said, I started developing this module, I guess it's roughly 5 years ago now. And that was when most of the work of this module was implemented, but it has been kind of a side project through the years, and it has been updated once in a while after that as well. So Knut-Andreas mentioned the UPR module briefly, and the UPR module is a module in MRST that is used to create more advanced types of grids. So the default or the grid structure in MRST is extremely flexible, and you can implement most types of grids in it, from simple simplex grids to structured Cartesian grids, and all the way up to complex corner point grids of real reservoirs, as you saw an example of in Knut-Andreas' talks. However, in order to create these more advanced grids, requires quite a bit of manual labor if you want to use only the core module in MRST, especially if you want to do grids that are having some kind of adaptations, for example, local grid refinement or adaptations to faults or fractures or wells. And this is where the UPR module started, really. It's the main idea of the UPR module was to create grids that were where you were able to create grids that are conforming to faults and fractures, but also to have a module where you could easily create the grids of non-convex domains, grids with wells and local refinement of the grids around the wells, and a module that could create relatively complex grids without you having to do a lot of coding or manual implementation yourself. So I'm going to talk to you today about some of the key aspects of the UPR module. I'm going to talk to you a bit about the optimization of the grids we are using in the UPR module. And the main focus of the talk will be grids conforming to different constraints, both phase constraints and cell constraints. And I will come back to that a bit later in the talk. The UPR module is based exclusively on so-called PEBI grids, or perpendicular bisector grids, as you can see an example of in the picture. These types of grids also have a lot of different names. Maybe most commonly is Voronoi diagrams or Voronoi tessellations. But in the UPR module, we ended up going for the PEBI grid name, mostly because I guess that seemed to be the most used one in the petroleum literature. But the PEBI grid is defined by a set of points here. So you can see all of the cells have an associated points with them. And we call these points for sites. And when you're placing these sites in your domain, that will uniquely define your grid. And the way it's defined is that a cell around each site is the region in space that are closer to this site. So it's everything in space that is closer to the site than any of the other sites around it. These types of PEBI grids have a lot of nice properties. I'm not going to go through all of them, but one of them is that if you're drawing the vector between two neighboring sites, then it will be by definition perpendicular to this vector. So this is one of the nice properties if you're working, for example, with 2-point flux approximations. So this is showing the workflow from how you're using UPR, from you having the idea, I want a grid, until you're following through all the steps and you end up with an MRST grid in the end. And this might seem really complex and overwhelming, but it's really only one function you will need to know for most of the parts when you're using the UPR module. And that is this PEBI-grid 2D function. And this function is the one we will use almost exclusively today in this talk. And it's also a function that can be used to create the most of the grids in UPR. All of this, the other things are mostly for different types of specializations. The part here on the left is the workflow if you want to use a different types of optimization of your grid, CPG optimization. This part is the same thing, only for 3D. And maybe for some of you, the part here on the most right would be a bit of interest. This is the workflow for creating DFM grids in UPR module. But I guess this right part is maybe not as much developed as the gridding in 2 dimension, especially the PEBI-grid 2D part. So let's have a look at how we are creating a PEBI-grid in the UPR module. We can do this by calling the PEBI-grid 2D functions, and it takes 2 arguments. The first one here is the mesh size, mesh size. And that is basically telling UPR what the size you want of your cells. So it's the diameter of the cells, or at least the UPR module will try to create cells as close as possible to these sites. The second argument here is just the domain size. And the domain will start from 0, 0, and in the upper right corner, you will have 1, 1, which is what you're specifying here in the domain. But we can also do non-square domains in the UPR module. And you do this by specifying this keyword polyboundary or polygon boundary. And you supply a set of vertices. So we have the first vertex, the second vertex, the third vertex here. And these are just corresponding to the vertices around our domain. 1, 2, 3, 4, 5, 6, 7. So the last one here is 8. So this would be the last vertex around our domain. And you can then create a polygon by the vertices of the polygon. You just have to make sure you're sorting the points in your polygon either clockwise or counterclockwise. So I mentioned in the beginning that the Voronoi or PEBI grids are defined only by a set of sites. So in principle, we could only just, I guess, randomly place the sites in our domain, as we can see an example of here. The problem is that if you're placing the sites randomly in your domain, you're not really going to get really nicely shaped cells. So what the UPR module does is that it's running some kind of optimization from usually a randomly placed sites in order to get more uniformly shaped cells and nicer shaped cells. And you can see that an example here with the star-shaped boundary, we're just calling this PEBI-grid the 2D functions, and it will automatically do this optimization for you. Yes, and here you see just an example during the optimization procedure where we have the initial step without optimization, and here the sites are just placed randomly until the optimization is finished. I think it was something like 40 iteration steps. But the nicest thing here is that you don't really have to think about the optimization. We'll just give you out on relatively nicely shaped cells. But so we can actually create, if you just want to create a mesh of some domain, maybe some complex boundaries of your domain, you can use UPR for this, as you have seen examples of so far. You can also add wells and local refinements in areas you would like. But one of the main purposes, at least when we were developing UPR, was that we wanted grids that were conforming to faults and fractures. So this is what we have called phase conformity in UPR. And it means that when we are creating cells, we want cells here to conform with the phases along our constraint. So here we have the constraint in the dashed blue lines, and we want these phases here to align with these constraints. So instead of now just giving you the functionality in UPR for how you can create this mesh, I wanted to explain a bit about how UPR actually can achieve a conforming PEBI grids. So you can understand a bit more about what is going on behind the scenes of these more higher level routines in the UPR module. The idea is that you are first placing a set of circles along your constraints, and you place the circle center. So here is the center of each circle center. So here we are placing 4 circles around our constraint, and each of these circles have a circle center on the constraint. The next thing we do is that you are placing sites where these circles are intersecting. So these red dots here are sites. And we also need an additional site here on the tip of constraints in order to have a fully conforming grid. And this is actually sufficient for us to create a conforming PEBI grid. So here we have a grid just using these sites. So we have the first cell here, the second cell, third cell, fourth cell, and so on. But usually we would like to add, have more than, in this case, 4, 5, 6, 7 cells in our domain. So we can do this by just adding sites elsewhere in the domain. The only requirement we actually have on these sites is that these sites are located outside of these circles we created in order to make a conforming grid. So we are not allowed to place a site, for example, inside this circle here. So as long as these sites are placed outside of the circles, we will obtain a conforming grid. So you can see here that the faces here of this cell and this cell is on our constraint and so on. And then, of course, we can run some optimization again, and we obtain a grid with more nicer cells than if we're just placing them randomly. So here I'm going to show you how you actually can do this in using the standard functions in UPR. And we're again using the PEBI-grid 2D function. Here we have the mesh size, and we are saying we have a domain by size 1 by 1. And we're supplying the keyword here, phase constraints. And this keyword takes a cell array as input. So this is the cell array we are putting in. And this cell, each element in this cell array will be a vector of points. So this is the first point, which is the start of our constraint. And then we have our second point, which is the end of the constraints. And if you're supplying this to the PEBI-grid 2D function, we will end up with a conforming grid, as we can see here. But we can also supply several constraints and also intersecting constraints to this function. So here we see an example where we have two constraints, the first constraint and the second constraint. And these are just giving us two elements in this cell array. So we have here our first constraint, second constraint, and we end up, and the UPR module will create the grids here so that it's actually conforming also in the intersection of these two constraints. So unfortunately, I don't really have time to go into details in how this is done. But if you remember to the last slides where we were placing circles around each constraints, it's basically boils down to placing a single circle centered at the intersection and being a bit careful how you place the rest of them. There is some pitfalls you can go into if you're trying to just, especially if you want to create grids that are conforming to randomly created constraints, which you will have, for example, in a stochastically generated diffraction network. And I have here listed up three cases that can be especially difficult. The first case here is that where you have barely intersecting constraints. So you have this part here that is actually really small and much smaller than your mesh size. The way UPR handles this is that it's basically just cropping it away. So instead of having this X intersection, it will just create this Y intersection or T intersections instead. And it will basically, anyway, the UPR module will do this when the length of this segment is less than half the mesh size in this region. The sharp intersections is also handled in the UPR module automatically, and we'll talk about that in the next slide. But the last difficulty here or pitfall you can go into when creating conforming grids is not handled automatically in UPR. This is the case when the two constraints are really close and will kind of interfere with each other, but they're not really crossing each other. So this solution here is actually to do local refinement of the mesh, or you can do global refinement as well if you want to. But the UPR module allows you to do local refinement, but you have to do this manually and specify the regions you want to refine manually, unfortunately. So one of the issues if you're having very sharp intersections is that the sites you're placing, in this case along the upper constraints, will at some point start interfering with the sites you're placing in order to have a conforming grids in the lower constraint. Again, you can solve this by local grid refinement, but the way, let me just remove these sites again so we can, So again, you can get away with this by just refining your mesh sufficiently. But what the UPR module will do automatically if it detects that the intersection is too sharp and you have interference between the two constraints is that it will merge the two constraints. So you can see that instead here in the region around the intersection, UPR will merge the constraints in this small region here. And then elsewhere it will be conforming. So this is done automatically in the UPR module. So if this is not really the behavior you want, you will have to do something different. For example, you can, as I said, just refine your mesh in this area. And in figure A and B here, you just see what happens when the grid is, or the intersection is not sharp enough to really trigger this merging of the two constraints. So the second feature I wanted to talk about was the cell-centroid conformity feature in the UPR module. And the cell-centroid conformity feature is that basically, if in most cases you want that, I guess, would be if this is a well. So you have some well in your domain and you actually have some cells where you actually want the cell center to align to these constraints. So we want to create cells here where the cell centers of each of these cells align with our constraints. And you do this by passing on the keyword cell constraints into the same function, or the PEBI-grid 2D functions. And similarly to the phase constraints, we are just giving the constraint as a cell array. Again, you can give many elements to this cell array where each element would be a different constraints. And here you can see in this constraint, we have 1, 2, 3, 4 points, and that corresponds to this point, second point, third point, and fourth point. And of course, you can give as many points you want to your constraint in order for it to be at least look like it's don't have these kinks on them. So in the middle here, you see the grid that is spit out by calling this function, PEBI-grid 2D now, with the cell constraints. And you can see that the cells are more or less following our constraints. And the way the UPR module does this is basically just placing these sites here. So these red dots here, these red dots are sites then. So it's just distributing the sites along our constraints. And in that way, we get at least cells that have cell centroids very close to these constraints. But it cannot guarantee that the cell centroids, or what you get out when you call compute geometry in MRST, will lie exactly on the constraints, but it will be at least quite close. And then, of course, we can pass everything in at the same time and create a grid that is conforming to both phase constraints and cell constraints. So here we have our phase constraints, which are these blue and dash and red lines here in the grid. We have the cell constraints, which are the yellow or purple lines. And on the top here, you see the possibility to have a single point as a cell constraint. This would, I guess, be of interest if you have a vertical well going through your domain. And that is specified here. It's basically just giving the point and it will place a cell on this point. The last point, the last line here is the refinement, and it's specifying the refinement around the cells. So you can see around, sorry, the refinement around the wells. So you can see that around the wells, we have some sort of local refinement in this grid. And you could also, if you want to, specify local refinement around the phase constraints or anywhere you would like in your grid. So the UPR module was developed as part of a testing and prototyping when we were developing these techniques and workflows for generating Voronoi or PEBI grids conforming to phase constraints and cell constraints. But we realized that, of course, this gridding might be really useful for other users of MRST. So we have documented parts of the code and hopefully people will be able to use it. But it was never really developed to be a reservoir scale grid generator. And it was mainly developed to test your computer code on these more scientific test cases. And one of the known issues here in the UPR module is that it has a set of fixed absolute tolerances. So if you're, for example, trying to create a grid on the kilometer scale, it doesn't really, UPR module doesn't really take into account of the increased numerical rounding errors that happens if you're working on kilometer scale, and might produce a bit unpredictable results. So if you're trying to use the UPR module to create large grids, I would recommend you to rescale your domain, basically to try to get it as close as possible to the unit size. And then you can create the grid in the unit size. And then after you have created the grid, just rescale it back up to the desired size you want of your domain. So I've talked so far about the 2D functionality of the UPR module, but we also have some possibilities to create 3-dimensional grids. The simplest way is, of course, to create 2.5D grids, as you see an example of here in the middle, using the functionality in the core module of MRST. But we also have some possibilities to create the fully 3-dimensional grids that are conforming. Here you see an example of conforming to phase constraints, and here to cell constraints. This 3D functionality is not don't really have the same high-level routines as the 2-dimensional functions, and they're also, we unfortunately did not have that much time to fully develop these 3D methods. So they will probably require a bit more manual work for you if you want to create these types of grids. But you should be able to at least create some simple grids with, let's say, a few fractures or few faults in the domain, if you want to have that for just testing something else than a Cartesian grid. I finally wanted to mention a bit about where you can find the UPR module or learn a bit more about it. So the UPR module is included in as an MRST module. So this is basically the place to get it. You just download MRST. We have also written a book chapter in the new book Knut-Andreas talked about. And this is more of a user manual, and it goes a bit more, much more into depth than what I did today in this talk. And I guess this is the best place to learn about the UPR module, learn. We have also published a paper. This paper is not really specifically on the UPR module itself, but it goes into the mathematical details behind it and why the UPR module works and how you can actually create these conforming PEBI grids. And I guess this is the place to cite cite the UPR module if you want to use it. And I guess you can also cite this book chapter when that becomes available. And finally, the UPR module is also on GitHub if you want to find some bugs or have some requests or some questions or want to contribute. So with that, I think I will just thank you for your attention.
Thank you very much, Runar, for a very informative and educational presentation. There's a little bit of drilling going on in the background here, so if it's too bad, I think Fran will have to take over for me. But I think since we're now moving into the break, we'll allow for one question, and then I encourage you to continue the discussion and ask questions also in Zulip in the stream, which starts with TU3. So now the question I thought I'd ask you is from Luis Salgado. And he says, thanks for your talk. Is it possible to have curvilinear constraints, e.g. higher order polynomials in PEBI-grid 2D or UPR in general? I suppose you can always add several short rectilinear ones, but I was wondering if there is a direct way.
No, you will have to make it piecewise constant or piecewise linear. So higher order does not work, and it will not. The main, or there are several reasons for it to not work, but the main reason is that all the faces of these types of PEBI-grids are always straight. So you would always need some kind of piecewise linear in your final grid. So you can specify, of course, as many points you want in this piecewise linear, but in the end, it has to be piecewise linear.
Very good. Okay, so I hope, Runar, that you're able to monitor the Q&A in the
yes, of
Zoom
course,
stream.
I will.
Perfect. And then you can, of course, continue to ask questions and discuss there if you would like throughout the symposium.